So in the previous lectures, we discussed about dynamic programming. Now in this lecture, we'll discuss about an algorithm for dynamic programming. Needleman-Wunsch algorithm is a dynamic programming based algorithm. The idea here is to reduce the number of possibilities to be considered, but still obtain the optimal result. Hence, we are interested in finding out the optimal result without exploring complete possibilities or complete space of solution or each solutions, enumerating each solution. The idea here is to build up the best alignment by using optimal alignment or alignments of smaller subsequences, or we are trying to solve local problem or trying to align locally in such a manner that we get an optimal alignment globally. Here the idea, as I told you, is divide and conquer strategy. We divide the complete problem of alignment into a set of sub-problems. Each set of sub-problems are smaller in size, and there we can find solution in a relatively straightforward manner. Once we solve the smaller problem optimally, we'll discuss what does it mean by optimally in the next couple of slides. We'll use that solution and construct an optimal solution recursively for the original sequence alignment problem. So let's see how we can do that. Before we go that, what we are interested is using some kind of matrix, which is we call scoring matrix D, and we have to construct that scoring matrix for our two sequences. So typical scoring matrix represent all possible pairs of nucleotide from two sequences. It is similar to the graph we have constructed and shown in a Manhattan tourist problem. The dimension of this matrix or scoring matrix is n plus 1 cross m plus 1 when the lengths of the sequences provided to us are n and m. The element of this particular matrix or different cells of this matrix, if you think of, are constructed recursively using this formula, which I call a Dij element of this matrix, which are in Ai and J are indices, are constructed of maximum of these three equations. Here, if you look at it, the S is a substitution score, which is computed based on Xi and Yj element. Xi and Yj represent the nucleotides at ith and jth positions. We will discuss what does it mean by position in the matrix. And G is a gap penalty. So to understand this, we can take a simple example. Here I am interested in aligning two sequences AT and GAT. And these are the scoring schemes which we are going to use, where for the match we'll provide score of 1, for mismatch we'll provide score of -1, and gaps we'll provide -2. So first we have to construct score matrix where all possible subsequences, including an empty sequence or what we call gap for both sequences, are also possible. And then we initialize the first cell of the matrix 1, 1 with scored 0. So here I have constructed that matrix partially. So as I told you, we have n is equal to 3 and m is equal to 2. So we have constructed a matrix of dimension 4 cross 3. And these are the element of this matrix, which is 12 elements. We start with a 0 here, which is the first element 1, 1 scored as a 0. Then to represent the gaps, or two kind of gaps, one in the case of AT as well as in the case of GAT, I am going to travel in the downward directions and going to compute the scores. Since I'm moving, remember that the arrow indicates something different. Arrow does not indicate that where in direction of the movement. Arrow indicates when the score is computed from, which cell it actually computed from. So the first column, which is where you can see -2, -4, -6. The arrow indicates that when I move from 0 to this element, I'm aligning a gap with the G, which is basically -2 score. Again aligning gap with A, which is -2 plus -2, which is -4, and henceforth. Hence, in the first column, what we are doing is we are comparing the empty sequence to the GAT, and the alignment will look like is we are aligning gap with GAT. Similarly, when I move towards the first row, I am comparing AT with empty sequences or aligning with the gaps, and alignment looks like AT. And as I told you earlier that arrows basically talks about alignment for the subsequences. In other words, it says that this arrow indicates that this particular score has come from this particular cell. And when we go and talk about computing this particular element here, you will realize that we have three options. The score can be computed from here, score can be computed from here, and score can be computed from here. So we can actually look at the directions later on from this aspect, and we may have one or two arrows, or if possible 3 arrows, depending on the score. So we'll start with the element 2, 2. So we'll use this formula. Let me explain here again. I is equal to 2 and j is equal to 2. Now, if you look at carefully, x2 is equal to g, y2 is equal to a. Hence, therefore, the S of G and A, which is mismatch, will be -1. Okay. Now, what we have to do is we have to compute what is the score for this particular cell, which is 2, 2, which is equal to max of D 1, 1 plus S of G A D 1, 2 minus 2. Remember, gap is equal to -2. D 2, 1 minus 2. If we substitute D11 score, this score and other scores, we will get max of 0 minus 1, D12 is first row, second element, which is -2, -2. Similarly, another one is also D21 is also -2, -2. So we'll get max as a, here is -1, -4, -4. The answer is -1. So here the element is -1, and if you look at it, we have compared 3 scores. One derived from this element, one derived from this element, and one derived from this element. And we chose one which came from this cell. So the arrow will be in this direction. Okay. So the alignment here is now, which we are comparing here, is a G gap with G and A with the gap, and similarly A with gap and G with the gap. So So these three are we are comparing, and we are saying that this is the way the alignment works. This is the alignment. Now we'll go for the next table, which is this one. Okay. Again the same formula, same idea. Here I is equal to 2, j is equal to 3, and x2 is equal to g, and y3 is equal to t. Again we can compute 2, 3 is equal to max of d1, 2 plus sgt d1, 3 minus 2, that's a gap cost, and d2, 2 minus 2, which is again the gap cost. So we substitute the max of d12, which is minus 2 sgt, which is mismatch, so 1 minus d13 is minus 4 minus 2 d22, which is minus 1 minus 2, and this leads us to max of minus 3 minus 6 minus 3. The value here is going to be minus 3. Now you realize now that there are two computation leads to minus 3, and for that what we have to do is we have to actually put value of minus 3, and now we have to trace back where this value is computed from, which cell contributes towards minus 3. So if you look at it, cell D22, so there will be arrow here from here, as well as D12, which is this arrow. Okay. So we have two arrows. So it gives you an idea, and here we are comparing following alignment: AT with gap and GT, AT with G gap, AT with G gap. This makes the computation of scores in the cell of this D matrix or scoring matrix straightforward. Now we'll do similarly and complete the scoring matrix. Now we have a set of arrows and set of values. What is the next steps? So what we are interested in is answering the question of how to generate the alignment from the score matrix. And now we are at the end, and there are a set of arrows. We can take help of arrows to trace back the path which allows us to get the best optimal path using this score matrix. So Traceback is very much part of Needleman-Wunsch algorithm, and what here idea is we want to deduce the base alignment from the score matrix. So what we will do, we'll start with the last element of our matrix, which is our last cell of this matrix, which is this one. This is the element, and we have to go to the first element. And what we are saying is, can we find a path from this to this element? There are also possibility of multiple paths, but can we find the path from the last element to the first element, or the last cell to the first cell of the matrix, so that we can get the best alignment. So there are three possibilities. As you can see, there are three kind of arrow. One is up, left, and diagonal. So diagonal basically goes from the top left corner, is up or left. So we have a possibility of going again diagonally, up or left. So now let's use this three kind of arrows and trace back. So rules are simple. If we move diagonally, the letters from the two sequences are aligned. Remember, align does not mean they match. It's just that I am aligning two letters. If we move left, a gap is introduced in the bottom sequence. If we move up, the gap is introduced in the top sequence. And alignment is built from the back to front. So we are going from, remember, we are going from the bottom cell to the topmost cell. So we are going from the back to the front in case of alignment of the sequences. So let's start and see how we can do it. So here we are moving from 0, 0 to 1. Okay. So what we have done is, we have diagonally two nucleotides are aligned. What are those two nucleotides? Here is a T and T. So alignment here is TT. Now we are going to move from this one to this one. Remember is that here the life is easy because there is only one arrow we have to trace. If we have to move here, there are two arrows. So here it's easy, straightforward. So we go from -1 to -2, this cell, and this is again a diagonal. So we already follow this path. Now we are going to follow this path, and alignment is going to be AA. Now when we come here, there is only one arrow which is remain here. So we have to move here, and we are going to move upward and going to introduce sequence, a gap in the sequence. So again, we have introduced a gap in a top sequence, and that's why we have a gap and the G. Hence we found a path which is optimal here. Okay, which actually is, and this is our alignment, and our alignment is complete when we reach to the first cell, and we got our aligned sequences. Now let's take another example, bit more complex example. Here we are also changing the scoring scheme, which is more towards practical applications. Here you can see that C, T, A, G have a different score when it comes to mismatch. Gap, we are going to use constant gap for simplicity. You can use a fine gap penalty also for simplicity, for more practical purposes. But here currently we are using -10 as a constant gap penalty. And for the mismatch, as I told you, here is a negative values, but for certain mismatch it is not negative value but lesser value. We have two sequence here. First sequence length n is equal to 4 and m is equal to 6. So the scoring matrix D will be of size 5 cross 7. Now here I have already constructed the akin to the gaps or empty sequences both sides. So we have filled first row and first column. For the sake of completeness, let me put all the numbers here so we can do computation without much difficulty. So we initialize the 5x7 score matrix. We have first row and columns are initialized with the gap penalties, and as we discussed, this represents the score of the sequences with respect to the blank sequences. Then the objective is to fill the rest of the cells according to the formula we used earlier. Let's do a couple of them. So we'll start with the 2, 2, and let me show how we computed -1. So here again the formula D22 will have a D11 plus xi or x2 and y2, which is j, and here we have a D12, D21 plus g. So here we have a mismatch penalty. D11 has a score of 0, so -1, -20, -20, and we got -1, and hence we have a -1 as a value. Now we again go back and compute this element. Now here we did the same task. Here we have a 1, 2, 3, 4, 5, just for visualization. It would be nice to see which element we are computing. We are trying to compute this element, and I'm trying to show why we used or got -8. Fill the cell at 2, 3 using the formula is the we are doing it. D23, I3, 1, this should be 2, 1, 2 plus S T T, because here there is a T, there is a T here. So we have a -10 plus aligned, which is 2, so -8 answer. Similarly, D13 is -20, T is aligned with gap, it is G -10, so we got -30. Here with D22, which is -1, and the gap which is -10, so we got -11, and finally we got a -8 as an answer. And this -8 is computed from 1, 2 elements, so there is an arrow from this side. Remember, this is not an arrow, so that's an interesting fact. Similarly, we can compute the score for remaining cells and fill the cells with the remaining scores or computed scores and the arrows which we actually need for computing score. So arrows describing which cells from this score has come from, and we have this kind of scoring matrix. Now the question is again how to find the best alignment. So we'll start again with the last cell of the matrix and go further with the path we can follow using the arrow. So here we start with -15. We are going to the -5 because this is the way arrow has been constructed. Then we go towards -7. So here when we do this arrow, it is basically introducing left side, so gap in a bottom one. Then again we'll do it. We obtain the value 5 from the diagonal cells, and therefore we are going to move diagonally up, which means there is alignment, and here you can T and T are aligned. So alignment now will be TG, T gap. Remember, we are going in this direction. So I can go back again and look at the alignment where the arrow came from, and you can see that this is the complete alignment here, where this arrow has been used. After that, this arrow, and this arrow. And the optimal alignment we are getting here is GTACTG, gap TAGT gap. So we have moved this direction, and you can see that C aligned with G, A aligned with A, this one says T aligned with T, and G aligns with the gap. And also remember that there are multiple tracebacks are possible. In these examples, we have not seen those kind of tracebacks at all. We have seen multiple possibility of arrows, but not traceback. But in practice, it is possible to have a multiple tracebacks. So let me summarize Needleman-Wunsch algorithm. The alignment is over entire length of two sequences. That's the main idea in Needleman-Wunsch algorithm. Traceback start from the lower right corner of the scoring matrix and complete in the upper left cells of the matrix. So that's how we get a tracebacks. And in certain examples, there are possibility of having a multiple tracebacks. What is the advantages of using Needleman-Wunsch algorithms? It can be applied regardless of the length of two sequences or the complexity of the two sequences in terms of gaps, in terms of mutations. It finds the best alignment of two sequences that are of similar length, not the same, similar length. So that basically solves typically global alignment problem, or it is suited for solving global alignment problem.